Thanks a lot for the invitation, and my really sincere apologies that I couldn't make it in person to Trento. And it is really my pleasure to talk to you about one of my favorite topics, the production of charm and non-charm nuclei at LHC energies. So in order to introduce a bit the topic, let me remind you of like the basic nuclear physics classes that in fact many of you teach at university. And what you then always show is the table of nuclides, so the proton number versus the neutron number, and then you place their all known nuclei. And now what has been done at the LHC in the last 10 years, but also at RIC and even starting a bit already at lower energies, is to extend this table into the antimatter direction. So there have been the discovery of the anti-alpha at star. There have been extensive measurements by ALICE on helia, also anti-alpha, anti-helium, anti-deuterons, and so on. In fact, this can be further extended in the strangeness direction. So you can replace, for instance, in the triton, which is a proton, or in an anti-triton, which is an antiproton, and two antineutrons. You can replace one of the antineutrons by an anti-lambda, so an anti-D, anti-U, anti-S quark, and then you get something like the anti-hypertriton. And in this way, you extend this chart in the third dimension. And now what I will talk about in this talk is really to add a fourth axis to this plot, namely the charm direction. You can guess that. And I think what is the good perspective in all this is that at the LHC in the next 15 years, we will really be able to do this. Now, so it's really a whole zoo that we are addressing here, and which we have already addressed. And as I mentioned, this is really forming a long-term program. So what has happened in run 1 and 2 at the LHC was to measure really the light anti-nuclei, anti-deuteron, anti-triton, anti-helium-3, and then also the first anti-hypernuclei like the anti-hypertriton, and we came up to the anti-alpha. Now, with the upgraded detectors and increasing luminosity, especially in ALICE, there will be measurements of A equal 4 antinuclei like anti-hyperhydrogen or anti-hyperhelium. And then really, especially starting in about run 4, but then for sure in run 5 and 6, we will measure the nuclei with charm, so bound states of lambda C and neutron, like the C deuteron or the C triton, a lambda C bound to 2 neutrons. And the ideal tool for this, and I will discuss this in detail, will be the ALICE 3 detector, which is a new experiment planned at the LHC point 2, which should take data in run 5 and 6. Now, what you always have to keep in mind to set the stage a bit is these particles are very, very rarely produced, even the non-charm ones. And what always is the key number to keep in mind is what we call the penalty factor. So about 5% of all particles that are produced in PP or lead collisions at the LHC are protons or antiprotons. And then for each additional nucleon, like going from the antiproton to the antideutron or the anti-helium-3 or the anti-alpha, the yield or the production rate decreases by a factor of 350 in heavy ion collisions. And in PP collisions, the penalty factor is even larger. It decreases by a factor of about 1,000. Okay, and this always then really tells you the enormous luminosity requirements that we have in this physics. Now, this penalty factor, it has in the statistical thermal model a very, very natural explanation. So, I mean, Anton will, of course, discuss the statistical model in great detail in the next talk, so I can be a bit brief here. But if you plot the observed particle yields normalized by the spin degeneracy as a function of the mass, you of course see that light particles are abundantly produced and heavy particles are of course suppressed. And you can quantify it very roughly. I mean, in detail, it's a Bessel function, but very roughly it is an Boltzmann factor, which is just the mass divided by the temperature, and the temperature we observe for all particles is 156 MeV, and this Boltzmann factor, if you plug in then for one additional nucleon, the proton or neutron mass here, you have temperatures in the 150 to 160 MeV range, you get exactly these penalty factors of around 300 to 400. Now, the surprising thing is, and that is still also a subject of research, but I will not go into detail here, is that this works very well also for this zoo of antinuclei and hypernuclei, which I have shown. You see the helium-3 hypertriton perfectly falling on this curve, even though their binding energy is much, much smaller than the common freeze-out temperature. So the binding energy of this object is just 2 MeV, while the common freeze-out temperature is 160 MeV. And yet this works very well. So for that reason, there are currently in the community many ongoing discussions. Is there alternative production scenarios? There is, of course, the coalescence model. You heard about the Quark coalescence just in the talk before, or there is the idea of continuous generation or destruction via hadronic interactions in the hadronic phase. But all this is, for my talk here today, not really relevant. While also me personally, I spend a lot of time understanding this. The essence of what I want to tell you is, or what is relevant for what I want to tell you is shown in the right-hand side plot, where one of the most exotic objects that you can produce is the anti-hypertriton, okay? And it has a very wide wave function, okay? The lambda separation from the deuteron core is about 10 Fermi, okay? So it's almost as wide as a lead nucleus. And this results in a penalty factor in the coalescence, because this way you have to take the wave function into account. And this leads, if you normalize its production to helium-3 and you look at it as a system size, you see that in PP and P-lead collisions here at small multiplicities, its production is largely suppressed in coalescence models. While, for instance, in the statistical thermal models in PP collisions, it is not expected to be suppressed, and that will be also measured in the next years by ALICE. There are already some first hints that indeed there could be a suppression, but I mean this will be very interesting to measure in the next 5 years. But what you should take from this plot now for the discussion that will follow is that once you go to central heavy ion collisions where you produce 2,000 particles, where the system size becomes so large that I mean it really is really comparable to the object that you form. It's coalescence and statistical models, they give you the same answer, okay? And in fact, the same holds true even for this. If you have, surprisingly, it also holds true if you have continuous generation and destruction in the hadronic phase. There was a paper from Dima Olinichenko and Hanna Elfner and Volker Koch on this. And what you should look at here is the black curve, which essentially quantifies the yield change with respect to a thermal yield, depending on how late you freeze out compared to, I mean, in an expanding systems. And you see that the difference to the thermal model expectation is just of the order of 10% for the deuteron. So long story short, what I want to say is that you can believe in the thermal model or not. I mean, that is up to you, but what is clear to me at least is that once you go to a central heavy ion collision, it does give a very reliable baseline. And even if it was the case that it does not describe the microscopic mechanism correctly, it still gives you essentially the correct yields. Okay, and yeah, of course, Anton will discuss this more in detail. But I think this is what we should take away from this, and what sets us a good basis to study nuclei with charm like the C deuteron or the C triton. Now, as I mentioned, the The other good news is that at the LHC, we will also measure anti-hypernuclei now in the next 10 years with high precision. So A = 4 and hypernuclei, and maybe also at some point A = 5 will become in reach. And we have done detailed studies and projections for that. And this is all summarized in the yellow report. And why this is important, I will discuss in a minute. Now, let's look at these objects we want to discover, the C deuteron and C triton. So that are the lightest possible bound states you can imagine in the charm sector. So you just take a lambda C particle and you bind it to either one or two neutrons. And the good thing is also, while the lambda C is of course charged, the neutron is not, so you do not have any Coulomb repulsion. And already since the 1970s, their existence was proposed, but there have been since then many articles with like different opinions or different result in depending on the model if it's bound or not. But in fact, there is a good chance that the potential between charm baryons and nucleons is attractive, and that it's attractive enough to lead to a bound state. As a matter of fact, in the more recent calculations, it seems that it's more likely to find a charm nucleus is more likely the heavier or the more essentially nucleons are attached to it to keep the thing together. So maybe the C triton is in a current view more likely to be bound than a C deuteron. And all this point to make is that while it's of course would already be very sensational to discover these particles and to see the first nuclei in the charm sector, it is also of more fundamental interest to really understand the charm nucleon potential. In fact, an alternative way to study that is correlations, and also in ALICE we are specialists in that to do lambda C proton correlations, for instance. So this topic can be addressed from many sides, and but what I want to discuss here is really the possible observation of a bound state. Now, as I mentioned, the statistical thermal model will give us a reliable baseline. And the good thing is that, and as I mentioned, Anton will discuss it in detail in the next talk, in the statistical hadronization model, the yields of charm particles are, of course, and I have many more experts in the room than me talking about it now, are drastically enhanced because you have a large initial production of charm, which leads to an additional fugacity factor, and you essentially then enhance the production by a factor of 30 with respect to the non-charm particles. And you saw now you see here an extension of the plot I've shown before. Essentially, the yields normalized by the spin degeneracy as a function of the mass number. And you already saw before that, and now I show only here predictions and not the actual measurements, but you already saw before that the nuclei nicely fall on the curve for UDS particles. And then you expect the charm particles enhanced by one factor of GC, depending on how many charm quarks are in the baryon or meson that you want to produce. And you see here the C deuteron and the C triton enhanced by a factor of 30 with respect to the non-charm baseline. And what you also nicely see is how well these two physics cases of nuclei and charm particles connect, because in fact the enhancement with respect to the UDS only particles, you in the same mass range where you have multi-charm particles, you really only have antinuclei, and they really can provide, I think, a stable baseline over which the enhancement of charm baryons can be measured. And with this we can then look into how we want to observe something like the C deuteron. So as I mentioned, it is in fact a lambda C particle bound to a neutron, and the idea is essentially the particle gets formed in the collision, and then it just travels it leaves the collision zone and then travels to the detector, and then at some point the lambda C decays into proton kaon and pion, as it also does when it's unbound, with a branching ratio of around 6%. And then the idea is that for part of the decays, the decay proton can bind to the neutron that was originally attached to the lambda c, with the lifetime and the decay the lifetime of this decay would be the same 60 microns which the lambda c normally lives. Okay, now of course the decay momentum is quite large of the proton produced in the decay of the lambda c, but with some probability it can really bind to the neutron. Now, and it was nice to see also Andrea Rossi in the audience, because he was one of the first to work this out inside ALICE. That indeed, what we can do is we can look at the momenta with which normally deuterons are formed in the collision. So, for instance, here you see the deuteron yield normalized by the proton yield and the calculation from the Frankfurt group, and you see they can describe the deuteron data of ALICE by requiring that the momentum difference between a proton and neutron is around 280 MeV. So you can play the same game. You can look at the lambda c decay at rest. You look at the proton momenta. You look at the fraction, which is below 200 MeV, and then you find that this is around 3 to 10%. So, but that also shows you, despite this factor 30 enhancement, which we get from the charm fugacity factor, the analysis is very challenging, because and then you get first penalized by the rather low branching fraction of the lambda c decay, and then in addition by the fact that you have to bind the proton to the neutron so that you can observe a deuteron in the detector, and because experimentally neutrons you cannot detect. But I mean, also here the beauty is really that we can have a completely self-consistent physics program with the coalescence momentum being constrained by LHC measurements and deuteron production, and then with this we get an idea on the branching fraction in lambda c decays. And if someone in the audience wants to do this calculation more properly and write a paper about it, I think that would be very much appreciated. Now, the other good news is that the detector upgrades, which will come for the ALICE experiment in the next 15 years, are ideally suited to do this measurement. So what will first come in the LHC run 4, so 2027 to 2030, is a new inner barrel for the inner tracker, which is ultra light, where the material budget is reduced from around 0.35% of radiation length to 0.05%, and where we will have a fully cylindrical geometry and a smaller pixel pitch. So that will really increase the precision with which we can measure the distance of closest approach to the primary vertex. But that will not be all. If the planned ALICE 3 detector will become reality in run 5 and 6, and you can find all information about this in this link here to the public workshop. You will have the first layer even inside the beam pipe at a distance of only 5 millimeter, and you will have a very good time of flight system for particle identification based on silicon. Also, you would have extremely good TCA resolution and extremely good particle identification over a large acceptance, and this would really be ideal to measure these particles. So I mean, you see here on the left the expected time of flight spectrum, and you see the distribution for deuterons here and for tritons here. They would be very well separated, so the decay products, also the kaon and the pion, can be cleanly identified. But the big thing the big challenge will be to reduce the background from primary antideutrons that will produce, that will pick up random pion and kaon pairs and will produce a big combinatorial background. Because as I mentioned, in contrast to like non-charm hypernuclei, which live like 7 centimeters, the the charm nuclei will only live like 60 to 100 microns. And therefore you need a very good separation, but you see that, for instance, with ALICE 3, you can nicely achieve this. So you see in blue here, the distribution of anti-deuterons coming from anti-C deuteron decays, and in red, the distribution of primaries. And what then one does in the analysis is one just cuts such that you only select, or that you select mostly the blue distribution here, and like this you can identify these particles quite cleanly. You see here some projections for the ITS3 in left as a function of expected of model expectations, also for different decay branching ratios, and yeah, you see that with ITS3 we will slowly get in reach of that, but significant. It will strongly depend on the actual production yields. But for sure, with ALICE 3 we would have for C deuteron significances of around 50, so we can really very cleanly validate its existence. And that brings me already to my summary and conclusions. So I've shown you that we really have very interesting physics prospects at LHC energies to observe for the first time charm nuclei. It's not only that we will get enormous luminosity from the machine, but also we will really have the right detectors to look into that. It's the first time that I give a talk at the Heavy Flavour workshop, but I think this probably also shows you that I do believe that there are very strong synergies between the core Heavy Flavour program, which will address more and more charm baryons, multi-charm baryons, charm baryons with strangeness. And I think that really anti-nuclei can provide a solid baseline to that, because you really measure particles in the same mass range. And the last point, which is probably the most important, there will always be discussions if these particles will exist or not, but for sure, I think what is the strength of the program I present here is that we do have a reliable estimates within some factor, of course, but we do have more or less reliable estimates on the expected production. So, and we will understand very well our efficiencies. So we can really then, if we don't see them, really also I think rule out their existence, because they should be produced in heavy ion collisions at the LHC. And that's all. Thanks a lot.
Thank you, Alexander. Questions here in the room? Online? Oh.
I have a very naive question, because of course I'm also teaching nuclear physics to my students, and then I explain this nuclear chart, and then they love me, and then the next session is I try to explain them why neutron is bound with a proton, while there is no bond state between proton and neutron, and then they hate me. And then basically I would like to ask the same, because you are only considering here nucleus or nuclei, where we would replace with a proton by the lambda c, but you're not considering those kind of hyper-exotic nuclei that could be formed by, for instance, having the equivalent to the neutron. You see the neutron plus a sigma c0, because then you do not have this Pauli exclusion principle anymore, and then maybe the force might be binding enough. I suppose it's been considered by the community. So what is the status about these hyper-exotics?
So in fact, also there are, different. You get sometimes. So who is most active in that is in fact the Japanese lattice community, and they do calculate these things. However, when they extrapolate to realistic pion masses, the situation becomes less clear. But what is for sure true is the particles I show here, which we want to address first, is only the tip of the iceberg. Okay, indeed there could be things like sigma C neutron. There can be things like di omega, so lambda bound states, which we to some extent have already ruled out, but not long-lived ones. But I think the thing is that it always needs a bit of work to then study what are the decay channels, can we observe it, and so on. But I think this all can be done. And indeed, I'm inviting everyone to provide predictions, not only on the yields with which these particles are produced, but also what are the promising decay channels. And then we can add them to this plot here. We stick them on it, and then we see, we will measure down these curves, and then we see if we find it or not. But I think indeed the thing is that there could be many surprises out there with exotic combinations that have not been seen so far. But what you always have to keep in mind is that sometimes there are coupled channels. Okay, like for instance. Things like psi neutron is not, is coupled with lambda, okay? And these things then decay strongly, and then they cannot be observed like that. So.
Okay, thank you. Questions on the web? I want to ask you, Alexander, you made the comment in the first part of the talk about the point that the statistical hadronization model at the end, if you look at large volume, is not so different from coalescence. I think I would agree if you mean that as with respect to the penalty factor that one can calculate in the statistical model. I mean, the point is, if you move from one particle to the other, you can have a factor 300 or 400 suppression. You find that both in coalescence and in statistical hadronization model, in the sense that one can be 320, the other can be 380 at that level. You mean something at that level?
Yes, absolutely. Yeah.
Okay.
Absolutely. But you see, in for hypertriton, in PP is a factor 10. Okay. I mean, that's what you see here. You see a statistical model in orange and coalescence in blue. So there it can be a factor 10. So that's a calculation actually from Kaiji Sun and Che-Min Ko. Personally, I did a similar one. And I mean, but indeed, once you go to central heavy ions, it's more, as you say, 20%, 30%. And I think that is why I say that I think our baseline is quite reliable. Yeah. Now, what is probably more a challenge for the charm community present at this workshop is that I do not know if it has ever been studied in detail how big the influence of the wave function of the particle you produce is, because that's basically what causes this difference here for hypertriton.
Yes.
I mean, so this is something I was always wondering, when you freeze out from a 10 Fermi cube, if you are really still sensitive to if your D meson is 1 Fermi in width or half a Fermi, but I have no good feeling for that.
No, I can tell you, I have tried to look a little bit at that. And if you do coalescence, let's say in a quantum way, in the sense that you really relate the width in the R space and the P space, that depends on, you can have cases in which you go very close to the statistical hadronization model because you are not so sensitive to the radius or the width of the wave function, just because you have to compare that let's say with Q times the mass for the temperature, that is the thermal width of the medium. Yeah. If you are in a situation in which QMT is quite large with respect to sigma R, then you start not to be so sensitive. I mean, 30%. And then this may be the reason why. I think can be shown nearly analytically this point. But
yeah, I see. Okay. Yeah.
Okay, very good. Thank you again, Alexander, for
Thanks
the
to
very nice
you.
talk.